Okay, guys, we are going to prepare for the review. We've got the review here for the Chapter 8 test. This is Trig Identities, and just FYI, you will be able to use your Identities card, which has your unit circle and your identities on it for this particular test. It is a non-calculator test, so notice that at the top. And let's get rolling. We've got to go rather quickly here to make sure we get through this in a class period. You're going to use a lot of your just basic 8 identities for this first page, so we'll fly through that. I'm going to go quickly. For those watching the video, you can always stop, rewind, pause, slow down, whatever, as needed. We may have some people ask questions in class here today as well, so just bear with us if we have a question in class. I'll repeat that question so that you'll get the same question and answer session that we have here in the class period. The first one's a pretty simple one. 1 over cosecant is just what? It's 1 over, it's basically sine, isn't it? So the first one's easy. That is sine x. Okay, easy enough. All right, and then we have the second one, and the second one is also fairly simple. We have the bottom, which will turn into, let's do different colors here that we can keep this separated. We're going to have sine x, cosine x on the top. We'll divide that by, this at the bottom actually is one of our Pythagorean identities. This is sine squared x. And so our sine and one of our sines on the bottom will cancel. That will be cosine x over sine x. And we know that to be also just cotangent. Cotangent x. And so that is the answer to number 2. Number 3. Number 3 we have... let's see here. If we take sine squared over cosine squared, that's just tangent squared. So 1 plus tangent squared x. And that is also another one of our Pythagorean identities that we can use to give us secant squared x. And that is the answer to number 3. Okay, number 4. Number 4 is... if we take this right here, this is actually another Pythagorean identity, the same one we used on number 3. And so we're going to have the square root of secant squared x, and square root of a square is just the actual thing itself. So we have secant x, which is the answer to number 4. Okay, moving right along. Number 5, we have the square root of 1 minus sine squared x, and we could find out by using another Pythagorean identity that this is basically this is cosine squared x. And once again, just take the square root of a square, and it is cosine x. Cosine times secant. Well, this is the same thing as cosine x times 1 over cos x. And so those cosines would just cancel if you just put that over 1. So this is simply 1. Using the pure identity of secant squared x minus tangent x, again, we're just using this little card here, our identities sheet here. We're using just identities that we've got here on this page. So we've got secant squared minus tangent squared. If I took this and moved tangent across, I just have 1. There's nothing much to that one. 1 minus cosecant, 1 over cosecant squared x is actually the same thing as 1 minus sine squared x. And again, that is just cosine squared x. Using a lot of our Pythagorean identities in this first section. Number 9, tangent cosine. Let me move up the page here a little bit. Tangent cosine. On this one right here, we can change these. A lot of times, remember, it tells us a hint to solving some of these is just put everything in terms of sine and cosine to help you solve these. Your brain kind of works better in sine and cosine version, or cosine mode and sine mode. So if we change this to be sine x over cosine x times cosine x over 1, well, then our cosines would cancel and we just end up with sine x. Okay, forgive me, I haven't been changing colors here. So if we go back to number 10 here, we've got cosine squared x minus 1. And I like to look at this, just kind of give you a visual here. I've got sine squared plus cosine squared x. If I did cosine squared x minus 1, if I move the 1 across to here, which would mean to minus it, right? And then I take the sine squared and put it over there, what's going to happen to the sine squared? It becomes negative. And so this is just a simple one step, negative sine squared x. Again, just using that Pythagorean identity. 6 sine x cosine x. This looks familiar. It looks like one of our versions of the double angle formulas right here, or identities. So we have 2 sine A cosine A. We don't have a 2, we have a 6, but we can get a 2 there by factoring out a 3. So I'm going to take and factor a 3 out. We end up with 3 times 2 sine x cosine x. And if you look at just this part of it right there, that is the identity for sine. So it is 3 sine 2a, the a is the angle, in this case it's x, so it's 3 sine x. So 3 sine x is our answer for number 11. I'm sorry, 3 sine 2x is our answer for number 11. Number 12, we're going to do a very similar case here. We have what looks kind of like the cosine double angle identity, but we need to make that a 2. We can factor a 4 out. So we'll end up with 1 minus 2 sine squared x. This is our cosine identity for cosine 2a, in this case 2x. So we'll have 4 cosine 2x. 4 cosine 2x. And so that would be the answer for number 12. Number 13, we can take, and again, when we look at some of these identities, you may say, well, Coach Williams, I solved it going this route with, different identities than what you're using, and that's fine. I'm going to go one direction. You may go a different direction, as long as we can end up with the same place and the same simplified, term when we get to these answers here, or when we get to proving and verifying answers in the future, that's fine. So if you go a different route, no problem. As long as you can show your work and show your identities match up, then you can get to the same place. It's okay if you go a different route. So here we go, tangent squared x. We can take that and make that secant squared x minus 1. So if we make the top secant squared x minus 1 over secant x plus 1, then we still have the plus 1. Now we can start to see there might be something we can do with this part right here. So maybe a possibility of having a difference of squares on the top, right? And that gives us one of these and then one with a minus, doesn't it? So if I took this top and said, well, that's a difference of squares, I've got secant x plus 1 times secant x minus 1. That's my top part, and now I can cancel out my secant x plus 1s. And so I'm just left with this secant x minus 1. Let me mark it out. Secant x minus 1, and then plus 1. So the plus 1 and minus 1 will cancel. So this just is simply secant x. Oops. Paper slid there a little bit. So it's just simply secant x for number 13. Number 14, we have secant squared x minus 1. That actually is a Pythagorean identity. That becomes tangent squared x over secant squared x. Now what we can do with this, we can actually change this. Again, change it to sine cosine, might be able to see this a little better. That's the same thing as sine squared x over cosine squared x, all over 1 over cosine squared x. When I take this bottom part, flip and multiply it, cosine squared x over 1, then my cosines will cancel, and I'll end up with sine squared x. Sorry for scribbling. My handwriting is not the greatest when we're going this fast. We'll try to make it as legible as possible and still maintain our current speed. We're moving along here to number 15. This one here, again, this is one of those that you could probably take several different approaches on. I'm going to work on the bottom, and I'm going to change this to be 1 over cosecant x. I'm going to change this one to be 1 over cotangent x. And then when I take both of those, as we did in this problem number 14, when I take both of these up and flip and multiply them to the top, well, then it's going to be cosecant x times cosecant x, cotangent x times cotangent x. And so I'm going to end up with this. I'm going to end up with cosecant squared x minus cotangent squared x. And using our Pythagorean identities there, we know that's going to be a 1. Okay, moving along to the next page. Use your identities to simplify each expression as much as possible. We have cosine 95 degrees times cosine 20 degrees minus sine 95 degrees, sine 20 degrees. And here we're going to use our sum and difference identities that you'll see on the bottom left of your card, because if you look, this is cosine, cosine, minus sine, sine. It looks very similar to this one here. Remember, cosine always lies. So if it's showing this in this part, then when we change it back to this, it'll actually be a plus sign. So this is going to be cosine of, and the two angles, the A and B angles, are going to be 95 degrees. Remember, this is just angle A. That's angle B. So it's 95. And this was a minus, so this becomes a plus 20 degrees. And so this is simply cosine of 115 degrees. That's not one of our common angles at this point, so I'm not going to ask you to simplify that down any further using your unit circle. We'll leave it as cosine 115. Number 17, very similar scenario here. We're going to use the same group of identities, the sum and difference identities. This is a sine cosine, and we call it flip-flopping, right? It flip-flops sine and cosine, and cosine and sine. And so this is a sine of a sum, because sine always tells the truth and it has a plus. So we have sine of two angles that are being added together. This is your A and your B. So we have pi over 6 plus pi over 2. Now, to get a common denominator, we'll multiply this by 3 over 3. And that will give us sine of 3 pi and another pi make 4 pi, and I love pi, so 4 pi's makes it even better, doesn't it? All over 6, because 6 is our common denominator. This will simplify to 2 pi over 3. If we look at 2 pi over 3 on our unit circle, we know sine is the y value, and so this is sine of 120 degrees. The y value here at this point is going to be the square root of 3 all over 2. And that's your answer for number 17. Number 18. This is a cosine one again. We have coses together, sines together, so we know it's a cosine. So we're going to have cosine, and then it's plus, so we know this is going to be a minus. Okay. This is 38 degrees, and this is 83 degrees. And when we look at that and subtract it, we're going to have cosine of negative 45 degrees. All right, and negative 45 degrees, again, using our unit circle. We come back around here. Negative 45 degrees is at 7 pi over 4. It's the x value when we deal with cosine. So this is simply a positive square root of 2 over 2. Positive because of the all-star trig class. This is for cosine being positive in that quadrant. Don't forget your all-star trig class trick to keep your positive and negatives correct there. All right, number 19, we're going to use the sum or difference of a tangent. In this case, remember, tangent is sine over cosine. So the top is going to be sine, which tells the truth. So the top one determines the sign of the actual sum or difference in the tangent. Because this is negative, we know this is going to be a negative inside. The bottom is cosine, and the cosine part lies, so it always is the opposite sign. So we look at the top for tangent. We see the sign is going to be the same at the top. This is a difference for tangent. And so our two angles are pi over 4, pi over 12. Conveniently enough, we end up just like we did at the top, multiplying by 3 over 3 to get a common denominator here of 12. And we will end up with tangent of 3 pi minus a pi, so it's 2 pi over 12, or reduced down to pi over 6. Tangent of pi over 6, if we look at our unit circle once again, pi over 6 is right here. It's y over x, so it's 1/2 all over 1 over the square root of, 1/2 over the square root of 3 over 2. 1/2 over the square root of 3 over 2. What's going to end up happening here is our denominators will cancel. We end up with 1 over the square root of 3. But we don't like this in the denominator, so we'll multiply that times the square root of 3 over 3. And our final answer here will be the square root of 3 over 3. All right. Moving on to number 20. We're going to verify, and this is basically doing some of our proofs, so we're going to verify that secant x plus cosecant x over 1 plus tangent x equals cosecant x. And these can get a little lengthy, and definitely will get lengthy in which way you decide to go as far as some of your identities. If you don't choose some of the shorter paths, it could get to more steps. But just keep plugging away. We're looking at your goal. Keep that in mind, and work with this side over here because it's a more difficult side. But work on that side there, trying to get as efficient as you can with your identities. Try to get to cosecant x in this case. I'm going to do the common, tip of just changing it to sine and cosine. In this case here, secant is going to be the same thing as 1 over cosine. Cosecant is 1 over sine. And on the bottom, I have 1 plus, and tangent is sine over cosine. At this point, I've got one term over here, and here I've got 2 terms over 2 terms. This is just a mess, isn't it? But to get to one term, I'm going to have to start combining some things together. So I'm going to try to get terms together on the top, terms together on the bottom, and see if I can't do some simplification. So I'm going to multiply and get common denominators on both of these. I'm going to multiply this by cosine x over cosine x, sine x over sine x. Here, I just need to multiply this by cosine x over cosine x. Okay, now that looks a little tricky and messy, but it's okay. We'll make it all work out here. We're going to have on the top sine x plus cosine x, and the common denominator we had is sine x cosine x multiplied. On the bottom, so we have just this on the top. On the bottom, we're going to have cosine x plus sine x all over cosine x. Now, we'll take this entire thing, right? Take this entire thing, bring it up, because remember, all this is still supposed to equal cosecant x, right? Take this entire thing, flip it over, multiply, right? We don't divide by fractions, we flip and multiply. So this will be cosine x all over. And is it okay for me to just rearrange this? We've got, sum is commutative, so we could just change the order here. Sine x plus cosine x. We're multiplying that, right? So we're taking that, flipping it over, multiplying. And then at this point, we can see that this will cancel with that right there. One of our cosines right here will go away. And I have 1 over sine x left. It's supposed to equal cosecant. Whoops, let me write that correctly. Cosecant x. And that is exactly what it is. 1 over sine is cosecant. So we have verified that this is correct. Okay, that's number 20. Let's move on to 21. All right, I hear the sighs in the crowd. Okay, we have this again, you may go a different route. If you've already done some of these, you may have gone a different route, but we'll use this route. It's one version, one option, but we'll definitely get down to the answer or the verification of this proof here. So cosine theta over 1 plus sine theta plus 1 over sine, or 1 plus sine theta over cosine theta. I'm just going to get a common denominator. We have one term, so I'm going to get a common denominator, see if I can get these together, see if I can't do some simplification down to one term. I'm going to have to multiply one of these. I'm going to have to multiply this side right here by cosine. That's an easy one, so I'm going to write over this. Cosine over cosine, and that way I'll have that times that on the bottom. That'll give me a common denominator there. I have to multiply this side by, and if I just bring this out, I'm going to multiply this side by 1 plus sine theta over 1 plus sine theta. Right? So I'm going to multiply that side by this here to get a common denominator. My result will be this. Let me hold this down. We're going to have cosine squared theta plus, and if I multiply this together, right, that's a perfect square. We square the first term, we multiply them together and double it, and then we square the last term. And that is how you take a binomial squared, and it's a simple way of just doing it without having to go through the other, longer method of adding your two middle terms together. It's a perfect square. It's the same term twice. We just double it. That is the entire top, cosine squared, and it's multiplied. The denominator is simply, and I'm going to leave it separated at this point too, cosine theta 1 plus sine theta. That is supposed to equal to secant theta. All right, now let's look at what we can do to try to simplify some things. Anytime I see cosine squared theta and sine squared theta, that's a Pythagorean identity. That is equal to 1. And I'm going to use that right off the bat. Those are going to go away. I'm going to have 1 plus 2 sine theta. That's 2 plus 2 sine theta. All over cosine theta 1 plus sine theta. Again, still supposed to equal to secant theta. If I factor a 2 out of here, I'll end up with a 1 plus sine theta. So I'm going to pull a 2 out. I'm going to have 2 times 1 plus sine theta all over cosine theta 1 plus sine theta. And, of course, those will cancel. This, again, is supposed to equal to secant theta. And 1 over cosine is secant, so this is 2 secant theta equal to 2 secant theta. And that has been verified. Completed that proof there. All right, number 22. Number 22, this is one that's going to be a little long just in writing everything out, but we have a cosine sum and a cosine difference. It's supposed to equal cosine x. So let's see what we can find out here and if it actually does indeed equal cosine x. So using our identities here again, our sum identities for cosine, we know that this is the same thing as, I'm going to start over here to the left a little bit, cosine pi thirds cosine x minus, because it's a plus, right? Sine pi thirds sine x. Then we add the next part. That was just this part right there. We're going to add the next part. We'll do it in different colors so we can see that that's what we're doing. So we have cosine pi thirds cosine x. And again, this one changes the sign, so this is plus sine pi thirds sine x. And if you'll look here, this positive sine pi thirds sine x and this negative sine pi thirds sine x will just go away. Don't forget, this is still supposed to equal cosine x. That's our goal. And here I have 2 times cosine pi thirds cosine x. What is cosine of pi over 3? If we look at our little unit circle here, cosine of pi over 3 gets us to right here. It's the x value. It's equal to 1/2. So 2 times 1/2 times cosine x is supposed to equal cosine x. Those cancel, and cosine x does equal cosine x. Moving on to 23. 23. We have sine x plus cosine x, and that's going to be squared, times cotangent x, and it's supposed to equal this over here, cotangent x plus 2 cosine squared x. I'm definitely going to go ahead and square this first binomial term. That's going to give me sine squared x, square the first term, multiply them together and double it, 2 sine x cosine x, and then square the last term. That times cotangent x is supposed to equal cotangent x plus 2 cosine squared x. All right, again, first thing I'm looking at is this sine squared plus cosine squared. I can get rid of that really fast. That's a 1. Right? Just replace that with a 1. So I'm going to have 1 plus 2 sine x cosine x. Okay, that's all that's inside, times cotangent x equals cotangent x plus 2 cosine squared x. I'm going to take cotangent and distribute it into both terms, right? All the way across to that 1. Didn't draw that far enough there. So cotangent x plus, and then at this point, I'm going to say this is 2 sine x cosine x, but I'm going to change cotangent to a sine or a cosine identity, right? Which is, what? Cosine x over sine x? So this is cotangent, but just in the form of cosine and sine. And that equals cotangent x plus 2, cosine squared x. If you notice, my sines on the second term here will cancel. I have cotangent x, right? Bring that down. I have cosine times 2 plus 2 cosine squared x. And that is exactly what we were supposed to prove or verify that it equaled. And so that one is done. Again, I know I'm moving fast, but we should have a pretty good idea of what's going on here. And if you're watching the video, you can stop or slow this down if you need to. Okay, let's go to the back. And don't forget the answers are on the back if you need to verify some of these and check my work. Make sure that I did them correctly. Number 24, if tangent of A is equal to 3/5, we know that tangent is y over x. And tangent of B, again, y over x is 1/2. Then can we find the values of tangent A plus B? And this is simply a sum and difference identity for tangent and plugging in the values once you have that form laid out. We know that tangent A plus B is tangent of A plus tangent of B. It's plus because the plus is what determines the top. Then it's 1 minus, flip the sign, tangent of A times tangent of B. Okay, now we just plug these values in. We're going to have, if we substitute in the 3/5 and the 1/2, we're going to have 3/5 plus 1/2 all over 1 minus 3/5 times 1/2. Okay, common denominator on the top. Obviously, we're just going to multiply this one times 5 over 5. We'll multiply this by 2 over 2. So we will have on the top 6 over 10. plus 5 over 10. On the bottom, if you think about the 1, we can make it a 10 over 10 because the other side is going to be a 10 for the denominator. 3 times 1 is 3, all over 10. So this is what we have at this point here. Combine your fractions, and you should end up with 11 over 10, all over 7 over 10. And we know the little trick here with common denominators with fractions here. Those just cancel. And we have 11 over 7. Okay? In this case, they're just going to let you leave it in that fraction form, not change it to a mixed fraction or a decimal. So that's sufficient for now. Number 24a is 11 over 7. 24b, this is just the difference version. So we're going to have, or the difference identity. So we're going to have tangent of a minus tangent of b all over 1 plus tangent of a tangent of b. Now, this follows the same pattern as this. It just changes the sign. So I'm going to skip, because they're all the same values. I'm going to skip straight to this step right here. We know we're going to have 6 over 10 minus, though, 5 over 10. It's just going to change the signs. All over 10 over 10 plus 3 over 10. Right? It's the same values, same locations, same denominators that we'll have to get, so we just jump to this step right here. We're just going to pull this in, right? Just changing the signs. And we could say plus minus if you want to, see that we just flip the signs around. All right, here we're going to end up with 1/10 over 7/10. Oh, sorry, 13. 13, my bad. 13. 13/10. And so we'll end up with, when we cancel our denominators, 1 over 13. And that is the answer for B. It's the answer for B. All right, 25. Suppose sine A is this, tangent B is this. They're giving us a few given information here for these two different angles. From that, we can derive what the other pieces of that triangle would be, the x, y, and the r. And we could find sine, cosine, and tangent. That's what our goal is. So we're going to take this right here. We know that this is y over r. We know that this is y over x. We also know where tangent's negative, where sine's positive, and they give us a little bit of information about where these angles take place. We know that we're going to have two angles, but it looks like they're going to end up in the same quadrant. Okay, we'll take this as angle A, and this one is angle B. This one says that sine, it says angle A is smaller than B, so wherever these happen in this quadrant between pi halves and pi, the second quadrant, pi halves and pi, right? They both happen between that. It says the two angles are there. A is smaller than B, so A would look something like this, and B would look something like that, right? Just in general, not to scale necessarily, but we know that sine A is 4 over 5. It's y over A. And so if I completed this triangle here, completed that triangle there, this one would be 4 is the y and 5 is the r. What's x going to be in this case? Because it's Pythagorean triple. It's 3. But we also have to remember this is a negative 3 because it's going in the negative direction. It says that tangent of this angle is negative 3 over 4. Well, we know it's y over x. And in this case, the x is what has to be negative. And this, again, is also a 3, 4, 5. So we know that r is 5. From that, we could go ahead and say, we know sine A is 4 over 5. Let me draw a line here to separate these out. We know cosine of A is x over r. So it's negative 3 over 5. Tangent of A is y over x, so it's going to be a negative 4/3. So we go ahead and get our setup, like get all of our values, correct? And then we could just take those and plug them in whenever we get to those identities over here with the sums that they're using for sine, cosine, and tangent. Here I know that sine of B is equal to 3 over 5. cosine of b is equal to -4 over 5, and tangent of b they already gave us was -3 over 4. Okay, so now I have all of my information I need when I go to start subbing in values for a, b, and c here. Let's go to work doing just that. So sine a is the sum identity, or sum identity here for sine. So this is going to be sine a cosine b plus cosine a sine b. Right? That's what we're looking for. And so let's just go plug in the values. We know that sine a is 4 over 5. Cosine b is -4 over 5 plus cosine a, which is going to be a -3 over 5. Sine b, it's a +3 over 5. And if we multiply those together, we're going to end up with a -16 over 25 plus a -9 over 25, which is -25 over -25. So it equals a -1. That's the answer to A. B, I'll change colors here again so we can see it. This is cosine. It's going to be cosine A, cosine B. It keeps them together. It flips the sign. Sine A, sine B. Plug in our values. Cosine A is -3 over 5. Cosine B is -4 over 5. We're going to subtract that, or subtract sine of A, which is going to be 4 over 5, and sine B, which is 3 over 5. And honestly, this is going to be a pretty easy one. +12 over 25 minus 12 over 25 is going to be a 0. It's the same thing minus each other, because once you multiply your two negatives, you get a positive. So we have 0 for B. Tangent, again, this is the one that's a little trickier as far as setting up. Just has more parts to it, but this is a plus one. So tangent A plus tangent B all over 1 minus tangent A, tangent B. Okay, so let's set up our fractions, just sub in our values. We have tangent of A, which is a -4 over 3. All over, or plus -3 over 4, all over 1 minus these two multiplied together. Well, what is this? I mean, that just becomes a +1, which is, I don't really care at this point what the top is, because the bottom's a 0. So this is what? It's undefined. It's something over 0. I don't even have to do the top to know that whatever it is over 0, it's not going to be 0 at the top. So it's something over 0. It's going to be undefined. Right? So that is the answer to number C. 25, if you look down here. Okay, let's look at the last problem. Suppose tangent of theta is 2/3, where pi is, or the theta happens between pi and 2 pi. So we're going to have this. It happens between here and there, and tangent is positive. Where's tangent positive? It's tangent's positive there and there. So we know it has to be in this quadrant. We know that it is y over x. So we know it's a -2 and -3. If I did my Pythagorean theorem to find out what the r value is, then I would find out that r is equal to the square root of 13. 4 and 9, which is 13. So r is the square root of 13. Again, I could build all of my values here, because we know that sine of this theta is going to be what? -2. I'm going to squeeze this in. Let's write it down here. Sine of theta is going to be negative 2 over the square root of 13. Cosine of theta is going to be negative 3 over the square root of 13. And then tangent, we already know what tangent is. It is 2/3. Negative 2 over negative 3, this gives us a positive 2/3. Okay, so we have that information, and now we can write in our little forms here for sine of 2a. Sine of 2a, our double angle identity tells us that it's really 2 sine of a cosine of a. So if we take and plug in our values, we're going to have 2 times negative 2 over the square root of 13 times negative 3 over the square root of 13. Well, 2 times a negative 2 is negative 4 times a negative 3 is a positive 12. And square root of 13 times square root of 13, anytime you square a square root, it just becomes what's underneath the square root sign, or the radical. So we have 12 over 13 for a. Cosine 2a, you can pick any one of the three. Remember, with cosine, there are 3 identities. We have 3 different ones. I like the squareds, and the reason I like the squareds is I'm dealing with a radical. And if I can square it, I get rid of the radical, don't I? So that's a fast way to get rid of the radical. So I'm going to go with the square. So we know that this is the same thing as cosine squared a minus sine squared a. Let's plug in our values now. Cosine was what? Negative 3 over the square root of 13 squared, right? That's the same thing as cosine a squared. Minus sine, which is negative 2 square root of 13 squared. Okay, so we'll square this. This will be 9 over 13 minus 4 over 13. And so we'll just end up with 5 over 13. And that completes the review. I know that was fast and furious, but we got through it. Again, if you need to stop, rewind, replay, slow me down, you can hit that little gear button over on the bottom right side of the video. There's a little gear button. You can change the speed there if you want to slow it down and just watch this in slow-mo. I know I talked. Probably if you slow this down to normal speed, you probably get like 2 hours of teaching because I talk so fast this thing. But hope you do well on the test tomorrow. Don't forget to study, and don't forget that tomorrow is also the notebook check for 8.5 and 8.6.